Mathematics is not about numbers, equations, computation or algorithm. It is about understanding. Hello everyone, welcome to the new module of Introduction to Group Theory. Myself, Navya Joy, Assistant Professor, Department of Science, the Bhopal School of Social Science. In this module, we are going to learn about the following topics. First, subgroups. Second, algebra of complexes of a group. Third topic is theorems on complexes of a group, and the final topic is criterion for a complex to be a subgroup. In last module, we have already learned about subgroup. So, we will go through the definition of subgroup. It is a subset H of a group which is called a subgroup if H forms a group with respect to the binary operation in G. That is, basically H is a subset of a group G. It is called a subgroup if it itself becomes a group. Now, we have seen its examples also, like if we consider G to be real numbers with respect to addition. We know that the set of real numbers have many subsets, like set of natural number is one of the subset of real number, set of rational number is one of the subset of real number, set of integers is one of the subset of real numbers, and even irrational number is also a subset of real numbers. So, now see n plus. Does this becoming a subgroup? No, we have already seen this in the last slides. Only q plus and z plus, among these three are the examples of subgroup. Now, what about complex of a group? Any subset H of a group G is called complex of a group. Now, we will see the examples of this. I have already told you that real numbers with respect to addition. We will consider the same example. Now, natural number is a subset of real number, rational number is a subset of real number, integers is also subset of real numbers. All this becomes n plus, q plus, z plus. All these are examples of complexes. It is not necessary that it itself should become a subgroup. So, what is the relation between complex of a group and subgroup? Every subgroup is a complex, but the converse need not be true. Example, we can see n plus, natural numbers with respect to addition. It is a complex of a group, but it does not become the subgroup because it itself is not a group. Now, we see the operations of complex. Mainly we discuss about two main operations. First one is multiplication of complexes. If we consider H and K are two complexes of a group G, then the multiplication of complexes works in such a way. HK will be equal to elements HK. That is, this particular set will contain elements in such a way x will be equal to hk, where h is coming from capital H and k is coming from capital K. And the inverse of a complex, if we consider H to be a complex of G, then H inverse will be equal to H inverse, where H is coming from capital H. Now, coming into the main theorem, algebra of complexes of group. The first theorem is, if H and K are any two complexes of a group, then we are supposed to prove that HK whole inverse is equal to K inverse H inverse. First, we will write down what is given to us. It is given that H and K are complexes, which means subset of group G. Now, other than that, what can be written? We will just write about the multiplication of these complexes. HK will be equal to, it will be containing elements in this format HK, where H is coming from capital H and small letter k is coming from capital K. Now, what about the H inverse? It will contain elements in such a way H inverse, where small letter h will be coming from capital H, and K inverse will contain element K inverse, where small letter k is coming from capital K. And what about K inverse H inverse? K inverse H inverse will contain elements small letter k inverse, small letter h inverse, where k belongs to capital K and h belongs to capital H. Now, what are we supposed to prove? To prove HK whole inverse is equal to K inverse H inverse. We will start from the LHS part. Let us consider an element from HK whole inverse. Let X be an arbitrary element of HK whole inverse. Now, how does the element look like HK inverse? It will be, X will be equal to small letter h, small letter k whole inverse, which is coming from capital H, capital K whole inverse. Now, we know about one of the law of groups, that is reversal law of groups. By reversal law of groups, what does it says? It says that for any elements of group G, AB whole inverse will be equal to B inverse A inverse. So, if we apply that particular rule here, this will be equal to what? K inverse H inverse, which is belonging to what? Capital K inverse, capital H inverse. It is very much visible from the definition of K inverse H inverse that it contains elements in such a way. So, now you see that the element which we have taken from HK whole inverse is belonging to capital K inverse, capital H inverse. So, what does this implies? This implies that HK whole inverse is a subset of K inverse H inverse. So, mark it as equation number 1. Now, we will focus on RHS. Let us take another element from RHS. Let Y be an arbitrary element of K inverse H inverse. So, Y will be equal to small letter K inverse, small letter H inverse. Now, using the again same rule, reversal law of groups, we can write this as what? HK whole inverse. So, it will belongs to what? It will belongs to capital H, capital K whole inverse. So, now you see the element which you have taken from K inverse H inverse is belonging to HK whole inverse. It means that K inverse H inverse is a subset of HK whole inverse. This is equation number 2. Now, from 1 and 2, what can be concluded? From 1 and 2, we can say that one is HK whole inverse is a subset of K inverse H inverse, and K inverse H inverse is a subset of HK whole inverse, which means K inverse H inverse is equal to HK whole inverse. Hence, proved. Now, moving into the next theorem. The theorem says if H is any subgroup of G, then H inverse is equal to H. Also show that the converse is not true. So, first we will write the information which is given to us. It is given that H is any subgroup of G. What do you mean by subgroup? Subgroup is a subset of group which already itself forms a group. Other than that, what information is given? When I say that H is in a subgroup of G, implies H itself is a group. Now, what are we supposed to prove here? We are supposed to prove here that H inverse is equal to H. We will solve this theorem also in a similar way. First, we will consider LHS. Let us take an element from LHS. Let X belongs to H inverse. We know that in H inverse element will be in such a form. Now, it is already given in this theorem that H is any subgroup. H is any subgroup of G implies that H is group. When I say that H itself forms a group, then it is supposed to satisfy all the 4 properties. That is, first one is closure property, second one is associative property, third one is existence of identity, and fourth one is existence of inverse. Now, if H belongs to capital H, then it implies that its inverse element also should belongs to what? Capital H. By which property? By existence of inverse. Now you see, the element which you have taken from capital H inverse is now belonging to capital H. What does this say? It says that H inverse is a subset of what? H. Mark it as equation number 1. Again, we are taking an element from capital H, that is the RHS part. Let H belongs to capital H. Now, we know that H inverse belongs to capital H. If H inverse is an element of H, then its inverse element should also belong to what? Capital H. So, what can be written? H inverse whole inverse belongs to H. Okay. Other than this, now see that by the definition of H inverse, if H inverse belongs to H, H inverse whole inverse should belongs to what? H inverse, by the definition of what? H inverse. So, what can be concluded from here? It means that H inverse whole inverse will be equal to what? H is belonging to capital H inverse. So, the element which we have taken from capital H is now belonging to capital H inverse. It implies that H is a subset of H inverse. Mark it as equation number 2. From 1 and 2, we can conclude that H is equal to H inverse. Why? Because H inverse is a subset of H and H is a subset of H inverse. That is why we have written H is equal to H inverse. So, the first part of the theorem is done. The second part is we are supposed to show that the converse is not true. Converse. What does we mean by the converse part? It means that let H be any complex of group G and H inverse is equal to H. It does not imply that H is a subgroup. This is we are supposed to prove in the converse part. H be a complex of group and H inverse is equal to G. We will prove this part using an example. Let us consider a group G is equal to 1 minus 1 and let the complex H be minus 1. Now, what will be the H inverse? What do you mean by H inverse? H inverse should be that particular element, that is minus 1 into what is giving you 1. It is exactly minus 1. So, the H inverse remains same, minus 1. Now, see, is this H inverse becoming a group? No. Why? Because by the closure property, minus 1 comma minus 1 be two element of H. Now, if I multiply this, what I am getting? 1, which is not a part of H, which implies that closure property is not satisfied. Which means that our converse part is not true. Now, coming into the last topic, that is criterion for a complex to be a subgroup. The theorem says that if G is a group and H be a non-empty subset of G, then H is a subgroup of G if and only if, this particular word is very important, if and only if A belongs to H, B belongs to H implies AB inverse belongs to H, where B inverse is the inverse of B in G. So, first we will write what is given to us. The information which is given to us is G is a group and H is a subset of G. Now, what are we supposed to prove? The proof of this particular theorem can be divided into two parts. Why? Because of this specific word. This word states that if H is a subgroup of the G, then this should hold. If this particular things hold, then this should be true. So, first part we will supposed to prove that if H is a subgroup of G, This is the condition that we are supposed to assume, and we are supposed to prove that A belongs to G, comma B belongs to G implies AB inverse belongs to H. In the second part, we are supposed to assume that A belongs to H, comma B belongs to H implies AB inverse belongs to H, and we are supposed to prove that H is a subgroup of G. So, this is the entire thing which we are supposed to prove. First, we will start with the first part. First part, let us assume that H is subgroup of G. And what are we supposed to prove? A belongs to H, B belongs to H implies AB inverse belongs to H. Now, what do you mean by that H is a subgroup of G? H is subgroup of G implies that H itself is a group. When H itself is a group, then it satisfies all the four axioms, that is closure property, associative property, existence of identity and existence of inverse. Now, by existence of inverse, what can I say? If B is an element of H, then I can say that B in the inverse also should be an element of H. Mark it as equation number 1. By closure property, what can be written? If A and B inverse are two elements of H, then their product also should be what? It also should be an element of this particular H. So, that is all about the first part. We have already proved that if H is a subgroup of G, then AB inverse will belongs to capital H. Moving into the second part, here we assume that if A belongs to H, B belongs to H implies AB inverse also belongs to H. This is the portion we have assumed, and what are we supposed to prove? We are supposed to prove that H is a subgroup of G. So, basically we are supposed to prove that H is a group. To prove a subset to be a subgroup, not subgroup, to be a group, we are supposed to show all the four axioms, that is closure, associative, identity and inverse. So, we will start with existence of identity. Let us consider two elements. Let A belongs to H, comma A belongs to H, that I have replaced A in terms of this particular B. So, according to the definition, what should I write here? A into A inverse should belongs to H. A into A inverse means E, that is the identity element. This implies that existence of identity property is satisfied. Moving into the next axiom, that is existence of inverse. Let us consider two elements. Let us consider E, which we have already considered now. Let E belongs to H, comma B belongs to H, be two elements. So, by the definition, what can be written? So, by definition, what can be written? E into B inverse should also belongs to H, implies B inverse belongs to H. What does this says? For all B belongs to H, B can be any arbitrary element. They will exist a unique inverse element for that particular B. This says that existence of inverse property is satisfied. Moving into the next property, that is closure property. Let us consider two elements. Let A comma B belongs to H. So, we are supposed to prove here that AB belongs to H. Now using definition, how can we prove here? We know that B inverse belongs to H, right? So we'll consider not B but B inverse. So let A comma B inverse belongs to H. So when we apply the definition, this will be equal to A into B inverse whole inverse belongs to H. This is equal to AB belongs to H. Thus closure property is satisfied. Now coming into the last property, that is associative property. There is nothing to prove here, since we know that for all A comma B comma C belongs to G, A dot B dot C is equal to A dot B dot C. Since H is a subset of G, basically all the elements of H is already inside this particular G. Since this particular property holds for all the elements of G, it is automatically holds for all the elements of H. Thus associative property is satisfied, implies H is subgroup of G. Hence proved. Hope this session was fruitful to you. Thank you.